Hello there, my name is Charles Msipa. I'm your e-tutor for MAT 1512. In this presentation, I'm going to try to sort of kill two birds with one bullet. By that I mean I'm going to try to use this, make you understand the squeeze theorem whilst I'm trying to explain and make you understand why the limit of sine over x as x tends to 0 is equals to 1. I think this is going to illustrate exactly what is stated by the theorem we refer to here as squeeze theorem. So let's start by looking at the statement of the squeeze theorem. We note that the squeeze theorem is an if-then statement. I highlight the if-then. In other words, if we've got these conditions satisfied such that is f of x less or equal to g of x less or equal to h of x, as x is approaching a point A. Remember, when we say calculating a limit as x is approaching A, we actually are not suggesting that x is ever going to be equals to A, because actually the function g itself may not be defined at that point A. So we're just looking at the limit as x is approaching A, not equals to A. So we can emphasize the, say, x not equals to A. So it says that then if we got this limit equal, then we can also conclude that the limit of g of x as x is approaching A is equals to L. Actually, we can illustrate this thing using a simple non-mathematical situation of this nature. Let's say you as a child, you're walking between your two parents, say father and mother, and you're walking in between there, and everywhere you walk, you keep yourself in between the two of them. So if there's a door here which both your father and mother is going to go through, and there's another door here, so if your father and mother go through this door, whilst you are also always keeping between them, you will also go through the same door. It cannot be that your father and mother passes through this door and you go through this door, but you maintain the fact that you're always in between them. So this is kind of illustrating in a non-mathematical way what the sandwich theorem or squeeze theorem states. So my target here is also to make you understand this limit, that limit of sine of x as x, sine of x over x as x is tending to 0 is equals to 1. Now, to understand this, I would like to make you to recall that, or sort of call attention to this kind of expression, that the limit of sine as x tends to 0 is equal to 0, and that of cosine as x tending to 0 is equals to 1. And recall that sine is actually a continuous function around the origin there. It goes like that, and the cosine, it goes this way. So, and we know that if a function is defined at a point and it's continuous, then the limit of that function f of x as x tends to A, and this function is defined continuous at A, then this limit is going to be equal to f of A. And as you can see here, 0 is actually equal to sine of 0. Same applies to cos. Cos of 0 is equals to 1. So they're actually in agreement with this kind of effect. So now, moving forward to convince you that this limit is equal to 1, I'll do it as follows. I hope by now you know that we can also measure angles using real numbers, and what we normally call radians, in such a way that if we've got like an angle or which is made by a straight line is equals to pi radians, and then before from there we should note the following. I've made this kind of sketch to use it to convince you about that limit. So let's start as follows. I've labeled here this angle theta, and also the segment from the horizontal to the circumference there I've labeled sine theta, and the arc between C and B I've labeled theta, and the length of this segment, which is tangent to the circle right where the horizontal crosses the circumference, I've labeled tan. So I would like now to convince you why I can claim, or we can claim, that this is tan and this is theta and this is sine theta. Remember that when you try right angle trigonometry, we can define sine of an angle by opposite over the hypotenuse. In this case, the hypotenuse is the radius of this circle, which in this case we can also take as y over r, where y is the coordinate of this point, and now the length of the red segment. And now since the radius is 1, this will be equals to y. Similarly, tan, we can define tan of theta as the opposite side here, which is CD over the adjacent side, which actually coincides with the radius, so which is also equals to 1, then that will be equals to CD. So the length CD is actually equals to tan, and then the length of the straight segment here is equal to sine, which is the y coordinate there. So now let's just find those labels there. Then this arc, we know to calculate the length of an arc, we can label by S and say the length of the arc is the angle multiplied by the radius. And again, the radius is equals to 1, so then the length of that arc is equals to theta. So as you can see, the length of the arc is actually the measure of the angle, and that is, because the length of the arc is obviously a real number. Then with that, looking at the arc itself, comparing with the tangent here, we can see that the arc theta is less than tan theta. So we have theta less or equal to tan theta. But theta also is greater, or this length, this arc, is longer than the red segment. So we're saying that theta is greater or equal to sine theta. Now, having this inequality, one idea we can use here, we can now divide both sides by sine theta. Not really both sides, the three terms involved here, you can divide all of them by sine theta. Then here, what we're going to get 1 less or equals to theta over sine theta. And this side can give this less or equal to tan theta over sine theta. But recall that tan is sine over cosine, so this will simplify to 1 over cosine theta. What we have here is tan, which tan in this case is tan theta is equals to sine theta over cos theta. So if we divide here by sine, this sign will simplify with the sign denominator, then put 1 over that. So now what we can fix our attention to now, we can fix our attention on this inequality, 1 less or equal to theta over sine theta less or equals to 1 over cosine theta. Now, at this stage here, before we introduce the limit, I would like to call your attention to the following. We know that 1 is less or equals to 2, and this is less or equals to 3. Now, if you invert all these numbers, we will see that 1 over 3 will be function with the highest, with the biggest denominator. So 1 over 3 will be actually less or equals to 1 over 2, and less or equals to 1 over 1. So doing the same thing here, if we invert this, we're going to get cosine theta less or equals to sine theta over theta less or equals to 1. So now we can see now that this expression, which we want to get limit of, actually we gave it at the beginning in terms of x, now we are doing in terms of theta. X and theta are not really different essentially, they are both real numbers, so that's fine. Then what we can do now, we can calculate the limit of this expression. So this is what we're going to do now. We have a sine theta over theta less or equals to 1, and less or equals to cos theta. Now, introducing the limit in this equality, we're going to have limit of cos theta as theta is going to 0 less or equals to limit as theta is going to 0, limit of sine theta over theta less or equals to limit as theta is going to 0 of 1. Now starting here, 1 is a constant. It doesn't matter whether theta goes to 0 or theta goes to 5 or goes to infinity. 1 will remain as a constant 1. So that limit there is going to be equals to 1. And then we have got a limit of sine theta over theta as theta is going to 0 greater or equal to limit of cos as theta going to 0. What we saw at the beginning here, what we discussed here, we have that equals to 1. So what we're going to have here, we've got this equals to 1. So what we have here, we have this limit squeezed between 1 and 1. That cannot mean anything else except that the limit of sine theta over theta as theta is turning to 0 is identically equals to 1. I sometimes use this three triple lines to emphasize that this limit must be identically equals to 1. So now I hope you are convinced that this limit is equal to 1. The reason why I'm trying to explain it emphatically and make sure that you understand this limit is because we're going to use it a lot in evaluating other trigonometric limits, and also when we get to differentiation, we're going to use it a lot in getting derivatives of trigonometric functions via the definition, or what is called the first principles. Otherwise, for now, I would like to say thank you for listening.